So a few of you have asked about this. I guess accidentally messed up, and I just assumed that when I imported the WebWork launcher from my winter quarter class, I thought it would link to this one, and it did not. So immediately after class, I'm going to go fix the WebWork so that you guys will have access to the right problem sets. So if you go into the WebWork launcher on Canvas right now, it's actually directing you to last quarters, which is why they're all closed and all that kind of stuff. So I'll get this fixed immediately after class. Everything for the full quarter is set up. So realistically, 15 to 20 minutes after class, you guys will have access to the WebWork, due Monday night, all that kind of good stuff. So my apologies for thinking that the import function was smarter than it actually is. All right, so today we are going to be talking about, let's see, basic electrical quantities. We also have a mini lab today. So I'm going to work the ICA with you guys as we progress through the class, covering the topics and all that kind of stuff so that we'll have time to do kind of both things. All right. So anyway, basic electrical quantities. So in this lecture, my goal is ultimately to define the different types of signals and things that we're going to be calculating and measuring in a practical sense in our labs and stuff like that throughout the class. I'm going to start with voltage because that's probably something you're more familiar with. And then we'll move on to charge, current, power, and energy. And I'm going to introduce a few kind of theorems and things like that along the way. So starting with voltage, the first thing that I'm going to do here is I'm going to give you a mathematical definition. And I want to start by saying we are never going to use the mathematical definition that I'm about to give you because it's related to electromagnetic field theory, and the overwhelming majority of you guys haven't had physics 202 or anything like that yet. So this is more of just kind of laying the framework for what voltage is, and then we're going to talk about it more in context of how we're going to be dealing with it in this class specifically. Okay. So mathematically, voltage can be defined, and let me have another little quick tangent here. So I'm using two subscripts here. So really what this is meaning is that the voltage seen between two different points in a circuit, where one point is what we would label point A, and the other point is what we would label point B. This is what's called a double subscript notation, and I'll go into a little bit more detail about how to read these in a little bit, but essentially I'm just letting you know this is just a difference in voltage between 2 points in a circuit, okay? So this is going to be equal to the integral from B to A of an electric field vector E dotted in to some differential line element DL. Okay. So as I said before, you guys probably don't have any electromagnetic field theory background. So this means next to nothing to most of us in this classroom right now. So I'm going to actually double down and introduce another field theory relationship so that we can actually bring this back towards something that we are relatively familiar with, okay? So there is what's called an electrostatic force, which I'm going to call F sub E. And this is the force that charged particles exert on each other, okay? And the mathematical expression for electrostatic force is Q, the charge of an electron, a proton, etc., multiplied by this electric field vector. So just really quickly, I'm going to define Q as the, sorry, that's a G. quantum charge, and this has a value of 1.602 times 10 to the negative 19 coulombs. So the reason why I introduced this concept of an electrostatic force is because if we divide that electrostatic force by Q, that is a way that we can represent that electric field vector. So I could rewrite this integral relationship as the integral from B to A of F over Q dotted into DL. And I can take this one step further, and I can take that factor of 1 over Q out of my integral. So that would leave me with 1 over Q times the integral from B to A of F dotted in to DL. So my question to you all is, what does the integral of F dot DL represent? Or another way to put this would be, what is force times distance? Work. Okay. So essentially, what this relationship tells us is that a voltage observed between 2 points is the amount of work required to move charge from point B to point A. Okay. We could rearrange this relationship slightly and actually come up with a relationship that a voltage, time-varying voltage V of t is going to be the derivative of energy, actually, with respect to charge. So I'm going to write down our first definition here, okay? We are going to say, from this mathematical expression, that voltage is the work or energy required per unit charge to move charge carriers between 2 points in a circuit. So voltage, from this definition, is what a physicist would typically call an electromotive force, okay? Because we need a voltage to be present somewhere in our system in order to cause electrons to flow from one part of a system to another part of a system. And that flow of electrons is what we're going to call a current here in a little bit, right? So we have to have voltages in our system somewhere in order for us to have current flowing in our circuit. Electrons won't move in any particular direction unless we apply a field and therefore induce a voltage. Yes. Carriers. Yes. So our second definition for voltage, and this is more the one that we're actually going to use in this class, is coming from the fact that we are using a line integral, right? So hopefully you guys have had enough calculus to know kind of what line integrals and things like that are. So we have essentially a conservative force, this electrostatic force here. And so that means that our line integral is going to be path independent, meaning it doesn't matter what route we take from point B to point A in our circuit, that difference in electrical potential or voltage is going to be the exact same thing. So from this line integral relationship, we can also say that voltage is the difference in electrical potential energy between 2 points in a circuit. So usually when I talk about the concept of electrical potential energy, students get a little bit confused, okay? This second definition, by the way, is the one that we are going to use really to handle voltages in this class. How many of you guys are familiar with the concept of gravitational potential energy? Hopefully, practically all of you, because you're in an engineering class, so you've had a physics class at some point in your life, right? So essentially, this pen right now has some amount of potential energy as it's sitting on top of this desk. If I pick it up, it has some different amount of potential energy due to the height difference between those 2 points. Well, there is electrical potential energy that behaves that way as well. So different points in a circuit will have different amounts of electrical potential energy, and we consider a voltage to just be a measure of that difference. For what it's worth, that is exactly what your multimeter is doing. When you connect it between 2 points in a circuit, it is just measuring that difference of electrical potential energy, okay? So this definition of voltage effectively just says if I choose any 2 points at random in a circuit, there will be some potential difference between them. Could be 0, could be 100 volts, it depends on the system, but that's how we're going to measure and quantify voltages, is just taking 2 different points and then seeing what difference of potential energy occurs. Okay, so let's talk about how we're going to represent voltages. Okay. So there are lots of different ways, say there are lots, there are really only 3 or 4, but so there are 3 or 4 different ways to represent voltage in a circuit. Now we are going to do this differently than you guys learned to do it in your Engineering 120 series, because I don't believe in that hippie delta V thing that they used. I want to have more specific information. So for me, as an electrical engineer, I would not consider a voltage fully defined unless it has both a magnitude. So if we had a AA battery, the magnitude of the voltage might be 1.5 volts. But I also need to indicate a polarity, okay? So if we take a generic circuit element like we were dealing with in class on Wednesday, like so, and let's say, just for the sake of argument, that this generic circuit element represents a AA battery, like we're familiar with from remote controls and things like that. The magnitude of this voltage would be 1.5 volts nominally. So there's my magnitude, but I also need to assign polarities. So I'm going to choose to put a positive polarity terminal on top and a negative polarity terminal on bottom. All these polarities mean is that the positive polarity terminal is at a state of 1.5 volts of higher electrical potential than the negative polarity terminal. That's literally it, okay? So generally speaking, bringing it back to multimeters and measuring voltages like you guys have done before, the red lead on your multimeter is generally used for the positive polarity terminal of a particular voltage, and the black lead on is used for the negative polarity terminal for any particular voltage. So how many of you guys in your prior classes accidentally measured a negative voltage? A couple of people are raising their hands saying they did. How did you make that negative voltage positive if you did? You swap the leads on your multimeter. And so we can do the exact same thing if we ever had a negative voltage. It just means that our polarity signs are switched. That's it, okay? So anytime you see a negative voltage in a circuit, it literally just means that the polarity that was assumed was incorrect to give you the positive result, okay? So when you're working problems in this class, if you're like me and you hate having too many negative numbers because you know you make simple algebraic mistakes and things like that, you can just swap the polarity to get rid of the negative sign, okay? So this particular representation where we have a magnitude and then a plus sign and a minus sign is the American style of representing voltages, okay? Now, you all may choose to watch YouTube videos from other people to help supplement your understanding of this class and all of that kind of good stuff. So I'm also going to introduce you to the European style of representing voltages as well. I don't like this particular representation because it's not how I learned it. And also it uses arrows, which I generally attribute to currents, but I'm going to show it to you just in case you happen to see it if you're, looking for help in circuits elsewhere. So if we take that same generic circuit element, we give a magnitude of 1.5 volts. In the European style, the negative polarity terminal of the voltage is the tail of the arrow, and it's usually a curved arrow like this. And then the positive polarity terminal of the voltage is the head of the arrow, okay? So let me just make a little note here. So this is, goodness gracious, my penmanship is getting terrible. So this is my positive polarity terminal. And then by extension, the tail down here is my negative polarity terminal. Now, as I mentioned earlier, I really don't like this particular representation, especially when you have currents and things like that labeled on your circuit diagrams as well, because there's just too many arrows and it can get a bit confusing, okay? So this is the European style. Another style of representing voltages that you'll see, we won't use it often in this class, but we will use it every now and then, is what's called the double subscript notation. And that's actually how I defined mathematically that voltage at the very beginning of the class, okay? So in a double subscript notation, I would need to label one of my terminals A or 1 or something like that, and the other terminal would also need a label. And so if we put our magnitude here of 1.5 volts, what we might write is VAB is equal to 1.5 volts, where the first letter in the subscript is the positive polarity terminal, and the second letter in the subscript is the negative polarity terminal. So this is a really clean way of writing voltages in systems where you don't want to have too much clutter on your schematic diagram, but it does require you to label all of your terminals, node points, and things like that, right? So if I wanted to represent the negative of this voltage, how do you guys think I might do that? I would flip the subscripts, exactly right. So if I wanted negative 1.5 volts, this would just be VBA, exactly right. So changing the subscripts is the exact same thing, or swapping the order of the subscripts is the exact same thing as multiplying by a factor of -1. I didn't happen to mention it for the European style, but how would we change the polarity of that voltage? Change the direction of the arrow. Okay, so these are the different ways that we might see voltages represented. In this class, I will use the American style roughly 99% of the time. And then every now and then we might see that double subscript notation, okay? Anybody have any questions about how we represent voltages? All right, so let's talk about voltage sources that we might see in this class. So the first voltage source that I'm going to introduce to you all is the symbol for a battery. So this symbol specifically is for a multi-cell battery or a battery pack like you guys might have used to power your Arduino and robots and all that kind of jazz back in your Engineering 120 series. We're not going to use this particular symbol too much just because if you're sloppy with how you draw things, you could accidentally think that this might be a capacitor because it's got parallel lines with it, okay? So it is a perfectly valid symbol. It's just not one that I choose to use particularly regularly, okay? So for a voltage source represented like this, the long horizontal lines correspond to the positive polarity terminal, and the short horizontal lines correspond to the negative polarity terminal. Now, batteries are DC voltage sources, so they will also have some magnitude, which I'm going to choose to represent symbolically here as just a voltage VDC. Okay. So this is our symbol for a battery. A symbol that we are much more likely to see in this particular class is this guy right here. This is going to be our symbol for a generic DC voltage source. So that includes batteries, battery packs, things like the voltage sources that we have around this room. You could use this to represent the 5-volt pin on your Arduino, whatever. This is just a generic DC voltage, okay? So we've just got this circle, and then we have a plus sign indicating which side is the positive polarity terminal for this voltage source, and a minus sign indicating which side is the negative polarity terminal for this voltage source. So all of the information is right there. Since this is a generic DC voltage source, I'm going to choose to write my magnitude as VDC yet again. So, let's see. The next voltage source that we are going to talk about briefly here is going to be an AC voltage source, okay? So my symbol for my AC voltage source is going to be essentially the exact same thing as my DC voltage source, except that I'm going to put this little tilde in the middle, which lets me know that the voltage provided by this source is changing in time, okay? So because we have a time varying voltage source, I'm going to choose to represent the magnitude of this guy with a lowercase VAC. So I use lowercase letters to indicate time varying signals, and I use uppercase letters to represent time invariant or constant signals. And I'm going to explicitly put here that this voltage is changing as a function of time, okay? So this is our generic AC voltage source that we're going to be dealing with a lot when we get to the third portion of this class. So these three different voltage sources are what are known as independent sources. Independent sources provide a fixed amount of a signal, in this case, a voltage, regardless of what is connected to the voltage source itself. So if I have a 5-volt generic DC source, it's going to provide 5 volts, no matter if I have it connected to 37 resistors, 5 capacitors, 2 inductors, whatever. It's going to provide 5 volts. It's a fixed quantity, right? I know it's kind of weird to think about the AC source providing a fixed quantity of voltage, but when we get into phasor representations, that'll make a little bit more sense. Yes, ma'am. So it's the same thing that we have for the generic DC, except that there's that tilde in the middle that's telling us that our voltage is changing as a function of time. So because I'm dealing with an AC voltage, I chose to express my magnitude using lowercase letters. So I use lowercase letters for AC signals and uppercase letters for DC signals. And I've explicitly stated here that this voltage changes as a function of time by writing it as a function of time. Okay, so these are the types of voltage sources that we are all relatively used to. So hopefully we're all pretty damn familiar with batteries at this point in our life. And whether you realize it or not, you're actually pretty familiar with these generic AC voltage sources as well, because anytime you plug anything into a receptacle in your home, that's actually what you're dealing with, okay? The generic DC voltage source, like I said, just represents any DC voltage. So it could be a battery pack like you guys have dealt with before, or it could be something like a DC power supply like you're going to be dealing with in this class, okay? So these are all things that we can regularly touch and interact with in our lives. The next two voltage sources that I'm going to introduce, they are dependent voltage sources, and they're really just a mathematical model to explain how some certain circuit elements behave, okay? So the first one that I'm going to introduce is going to be the voltage-controlled voltage source. Let me write that name down here really quickly. More commonly, voltage-controlled voltage source, so VCVS. So for this guy, instead of having a circle, I'm going to have a diamond, and now I have my positive and negative polarity terminals indicated here. Okay. So the diamond shape is used for what are called dependent sources, and I'll talk a little bit about more what that means in a moment. Okay. So in a voltage-controlled voltage source, essentially the output voltage of this source is dependent on some other voltage elsewhere in the circuit, okay? So we are going to express the magnitude for this voltage-controlled voltage source as K times Vx, where this quantity K is a scaling factor that has units of volts per volt, or you can consider it to be a dimensionless quantity, okay? And then this voltage Vx here is what's known as the controlling variable. So the output of this voltage source is dependent on the value of Vx, which is just some voltage elsewhere in the circuit that needs to be well defined. We'll see some dependent sources later on in today's class. That is correct. Volt per volt is the unit for that scaling factor. Okay. The last voltage source that we're going to deal with in this class, and this is going to have the exact same symbol, so this can get a little bit confusing. Is the current controlled voltage source. Or a CC VS. And the magnitude of this guy is going to be expressed as lowercase r times some current Ix, where this scaling factor of R has units of volts per amp, and our controlling variable in this case is our current, Ix. So essentially, this voltage depends on some current elsewhere in the circuit. Current, you guys remember from your engineering 120 class, is measured in amps. That current is multiplied by a scaling factor, which has units of volts per amps. So the output of this voltage source is, as we would expect, a voltage, because it is a voltage source. So those two symbols are identical to each other. The only way to tell the difference between them is if your controlling variable is a voltage, it's a voltage controlled voltage source. And if your controlling variable is a current, it is a current controlled voltage source. These guys are examples of dependent voltage sources because their output depends on some other quantity in the circuit. So just put dependent sources for now. All right, before we move on to charge and current, are there any questions about any of the topics I've introduced regarding voltages, voltage sources, all that kind of good stuff? Yes, ma'am. So that was a double subscript notation. Oh, thank you. I forgot to write that down. Thank you. Double subscript notation. Thank you for that. Any other questions? All right, so let's move on to charge and current. Actually, let's do current and charge. I actually just realized this is what happens when I don't bring notes to class. I technically forgot up here to tell you guys what the units of voltage are. So let me do that really quickly before we get onto it, right? So hopefully you're all aware that voltage is measured in volts, right? Where 1 volt, we can see from this definition where we're saying voltage is change in energy over change in charge, that a volt should be a joule per Coulomb. So those will be the fundamental units of voltage. Sorry for forgetting to introduce that 20 minutes ago. All right, going back down to my current and charge stuff. Sorry for that exclusion. Okay, so let's mathematically define current like we did a moment ago. So current I of t, so this is our time varying current, is going to be the derivative of charge Q of t with respect to time. So from this mathematical definition, we can see that our current, which is measured in amperes, an ampere is a coulomb per second. So charge divided by time. Okay. A kind of word-based definition for current is going to be current is the time rate of change of charge passing through a point in a circuit. So current is a measure effectively of how quickly charge passes. Now we can mathematically rearrange this expression, this derivative-based relationship for current to find that charge as a function of time is going to be the integral of current, where I'm integrating from T naught, where T naught represents some point in time where the amount of charge is a known quantity. So that is like an initial condition on our system. And we're going to integrate to some later point in time T that we're interested in. So the reason why I'm putting these prime notations on the I as a function of T and dt is because I can't have the same character in my function and that I'm taking my integral with respect to as in my limits of integration because it's just confusing. So that T prime is a dummy variable representing time. Now in your math classes, you might have used a Greek representation. So you might have used like tau or something as a dummy variable for time, but we can't use tau in electrical engineering because that has a very specific meaning for us that we're going to see when we get to the transient analysis portion of this class. So instead, I just use that prime designation saying like, hey, this is not the variable time. This is a dummy variable representing time, okay? It's just for clarity's sake, for mathematical rigor. We'll do a quick example here so you can understand what I mean by it. I also need to add one other little thing to this expression. So we need to add in the initial condition on our current as well. Okay. So the amount of charge accumulated depends not only on the current passing through a particular current element, but also how much charge was stored in that current in that circuit element when we started measuring. That's effectively what that mathematical expression means. Carter, what were you asking?
Is the function of that T of the same T that's with respect to I?
Yes. So that Q of T naught right there is just saying, hey, at some point in time when the current was known, that was how much charge I had.
That same T variable that is with respect to I and with dt?
No, so that's the T in the upper limit of the integration. Okay. Yeah. All of them are representations of time for what it's worth. So I understand that this can get a little esoteric and gross. I hope I can sort it out here in a moment with an example. Because this is something that this type of expression of using dummy variables is what we're going to have to do a couple of different times in this class. Couple of things I want to point out here because students tend to get a little bit confused. That Q of T naught term is outside of the integration. So that is literally just adding on some charge at the end because of how much charge was initially stored in the system, okay? So yeah, it is outside the integral. So that's why it's after the dt term. So the integral only goes up to the dt term, and then we add on the next thing. Let's work an example. Maybe this will make this slightly less confusing, okay? So let's say that this graph represents the current flowing through a particular circuit element measured in amps. Our horizontal axis will be time measured in seconds. And let's say that my current looks something akin to this. Actually, let me draw this less shittily. So we'll call this 0. This right here will be 2 seconds. This right here will be 5 seconds. This point right here will be 9 seconds. And this maximum value for the current is going to be 4 amps. Let's also introduce the information that Q at 0, so the amount of charge stored in this element at T is equal to 0, is 2 coulombs. And I want us to find the total charge accumulated at T is equal to, let's make it 4 seconds. So if we were to use our mathematical expressions here, we could say, for what it's worth, that I of t as a piecewise function would look something like, let's say, so let's look at that first interval from 0 seconds to 2 seconds. So I believe that we have a slope of 2 amperes per second because we increase 4 units in current over an interval of 2 seconds, right? So that's 4 amps over 2 seconds is going to look like 2 amps per second times time. Our y-intercept at this point in time is 0. So this is what our function looks like from 0 is less than t is less than 2 seconds. Can we all agree that that is an accurate mathematical representation of what's going on from this interval from 0 to 2? So what's going on over the interval from 2 to 5? Read the graph, it's 4. Right? Just 4 amps, constant value. So that's from 2 seconds is less than t is less than 5 seconds. And just for the sake of argument, even though we're not going to have to use it, we can define what's going on over the interval from 5 to 9 seconds as well. So pretty easily, I think I can see that my slope is going to be -1 because I'm decreasing 4 units in 4 seconds. So that's going to look like -1 amp per second. What I'm doing right now is I'm going to time shift this guy. So I'm shifting 5 units to the right. So that's going to look like t minus 5. And then my intercept at t is equal to 5 is 4 amps. Now, I understand that you guys may not have had much practice applying time shifting and all of that kind of stuff, since you probably learned it in your pre-calculus classes or high school or stuff like that. But effectively, anytime I have a simple linear graph like this, where it's some constant slope, usually what I do is I effectively just treat that where it starts as my new kind of zero. So that's why I have a slope of -1 based on the slope. T-5 indicates me shifting it over 5 seconds. And then I take my intercept to be whatever the value is at that T is equal to 5, which in this case is 4 amps. If you want to check our work here, if you plug in 5, we'll get a result of 4 amps. If you plug in 9, we're going to have -1 times 4 plus 4 is equal to 0. So it matches those endpoints, and it should match everywhere in between as well. So this will be over the interval from 5 seconds is less than T is less than 9 seconds. So if we wanted to use our mathematical relationship to determine our charge, Q at 4 seconds is going to be equal to the integral from 0 to 2 seconds of 2 amps per second times time with respect to time, plus the integral from 2 seconds to 4 seconds of 4 amps dt, plus my initial condition of Q0, right? So I've broken up my integral into 2 parts because I have a piecewise function. So I'm integrating fully over that first integral and all the way out to 4 seconds for that second integral. And then I'm adding my initial condition together. So what's the integral of 2t? T squared, right? So this is going to look like, so let's do this more formally. So we're going to have 2 amps per second multiplied by T squared over 2, evaluated at 2 seconds and 0 seconds. Then I'm going to have 4 amps. The integral of dt is just going to be t. So I'm going to have t evaluated at 4 seconds and 2 seconds. And then my initial condition was 2 coulombs. So I'm just going to tack that guy on here at the end. And if I keep on going here, this is going to look like 2 amps per second over 2. Then I'm going to have 4 seconds squared minus 0 seconds squared plus 4 amps times 4 seconds minus 2 seconds plus 2 coulombs. Continuing on here. So I've got amps per second multiplied by second squared. So that's going to look like amps times seconds, right? Well, if we look up here at the units, if current, an amp is a coulombs per second, then if I have amps multiplied by seconds, then my result is in coulombs, okay? So this is going to look like 1 times 4 coulombs. So that's just 4 coulombs. Then I have 4 amps times 2 seconds is going to be 8 coulombs. And then I have my initial condition of 2 coulombs. And this winds up 4 plus 8 plus 2 is 14 coulombs of charge. Now, realistically, this was mathematical overkill for this problem. Okay. Let me explain what I mean. in this class, a lot of the wave shapes and stuff that we're going to be dealing with are going to be piecewise linear functions like this. So when we integrate them, wouldn't that just be the area of this triangle as well as the area of this rectangle up to the point t is equal to 4? Wouldn't that represent all that work I did with my integral piecewise function and all of that kind of good stuff? So what's the area of that right triangle? So for a right triangle, the area is 1/2 base times height. So 1/2 times the base of 2 seconds times the height of 4 amperes. So that's 1/2 of 8 is 4 amp seconds or 4 coulombs. That's literally this part right here. What's the area of that rectangle? Well, for a rectangle, it's just base times height. So I have a base of 2 seconds, a height of 4 amperes. So that area is 8 amp seconds or 8 coulombs. And then I have my initial condition of 2 coulombs. So 4 plus 8 plus 2 is once again 14 coulombs. And we didn't spend 10 damn minutes doing calculus when we could have done the area of a triangle and the area of a rectangle to get the same result. Okay. So definitely use whatever mathematical technique is most appropriate to the problem that you're having. You can burn 20 minutes if you want to, throwing calculus at it, but if you can solve it using basic geometry, by all means, please do so. Save yourself the time and effort. All right, let's, so this was our integral-based relationship for determining charge from current. Let's go to our in-class assignment and let's look at problem number 1 and see if we can't use the derivative-based relationship to get current from charge. So I've given you a graph where once again we would have a piecewise function. We're not going to have to worry about all of that kind of good stuff here though, because we're only asked in this case to determine the current flowing through the element if our charge is given by this mathematical function. Remember that our current I of t is simply the derivative of charge with respect to time, right? So for part A here, we are asked to find the current at t is equal to 2 seconds. So 2 seconds would be this point right here. What's the slope of that line element? 0. So what's our current? 0. Because our derivative is nothing more than our slope, right? So we could see that at A, I of 2 seconds is equal to 0 amps because the charge is constant. For part B, we want to figure out what current is flowing at 6 seconds. So that would be that second X I've drawn. Well, now our current is changing. So we should expect to see some amount of, excuse me, now our charge is changing. So we should expect to see some current flowing through our circuit or our element or whatever it is. Since our charge is increasing, we should have an expectation that our current is going to be positive. Because this is just a simple straight line, taking the derivative of this is literally just the same as the slope, right? So what's the rise in charge that we see over the interval from 4 seconds to 8 seconds? So if we go all the way out to 8 seconds, we could just go from 4 seconds to 6 seconds if we wanted to, but I tend to use the end points of the line just because They're easily discerned from the graph without having to make any assumptions. So I would say that we're increasing from 2 to 4 as time increases from 4 to 8. So from that, I would say that I at 6 seconds is 4c minus 2c over 8 seconds minus 4 seconds, literally just my slope y2 minus y1 over x2 minus x1. And that comes out to be exactly positive 1/2 of an amp. Excuse me. For part C, we're out here at t is equal to 12 seconds. So this point right here. We're told how our charge is behaving as a function of time. It's 4e to the negative 0.2 times t minus 8 coulombs, right? So we're actually going to have to use our derivative-based relationship to get this guy, okay? So I at 12 seconds is going to be the derivative with respect to time of 4e to the minus 0.2 times t minus 8 coulombs evaluated at t is equal to 12 seconds. So how do I take the derivative of an exponential function? So if I had e to the alpha t, just generically here, and I want to take the derivative of this, what's the result? It's alpha e to the alpha t, right? So in this particular case, then, I'm going to pull down that factor of negative 0.2. Can anybody tell me what the units of that negative 0.2 need to be? So this is an expression, or it's a coefficient that's being multiplied by time, which is measured in seconds, okay? Our exponential function needs to act on an argument that is unitless, so that negative 0.2 there has to have units of per seconds for the units to cancel out and the exponential function to be acting on a dimensionless quantity, right? So anytime we have a coefficient being multiplied by time in an exponential function, you should assume the units are per seconds. I will try to explicitly tell you that as often as I can, but there wasn't really a good way for me to include that on this graph, so I wasn't able to do it, okay? So negative 2 per second. Then I'm going to have my 4 coulombs. So I've got coulombs per second. What's a coulomb per second again? An amp. So that's good because we're trying to find current. And then I'm going to have e to the negative 0.2, and I'm going to have 12 minus 8. So if we throw all of that into our calculator, negative 0.2 times 4 times, e to the negative 0.2 times 4. I wound up getting negative 0.35946, so I'm just going to call it 359 amperes. Does it make sense that our current is negative? Well, absolutely, because our charge is decreasing. So that's how we might go about using the derivative-based relationship to determine current from charge as a mathematical function. Any questions on this particular problem? All right. So let's talk about representing currents in circuits. So luckily for us, there's really only one way to do this. So if I have some generic circuit element A, like so, let's say that there is 5 amps flowing through this particular circuit element. In order for me to fully define the current, I need not only the magnitude, like I've written down, but I also need a direction, okay? So if I had 5 amps flowing down, how much current would be flowing up through the element? -5 amps, absolutely right. So essentially, anytime we need to get rid of a negative sign on a current, we simply change the direction that the current is flowing. Absolutely right. This is the only way that we'll see currents represented in this class. So that's literally just it. Feel like I had something else, but that's fine. All right, so let's now talk about current sources. So there are going to be 4 different current sources that we may see in this class. The first of which will be our generic DC current source. So this is an example of an independent current source, which is why we have the circle symbol. And there's just going to be an arrow in the middle of that circle indicating which direction the current is flowing. And then we are also going to have some magnitude, which in this case, I'm going to choose to write as IDC. So this is our generic DC current source. Then we'll have our generic AC current source. So same symbol, but now there's a tilde through the middle of it again to tell us that our current is changing in time. I'm going to choose to represent its magnitude as IAC, all lowercase. Yet again, lowercase letters are used for AC signals, uppercase letters are used for DC signals, and this will be changing as a function of time. So these are our independent current sources. Or let me just put it as independent sources, like I did the other one. So before we move on to our dependent current sources, I just want to bring something to your attention. Chances are nobody in this room except for myself and probably Dr. Niemrowski over here has actually physically touched a current source because they're not something that you regularly interact with. Most current sources or variable current sources and things like that that you might find are pieces of laboratory equipment that are usually pretty darn expensive, okay? More often than not, these current source symbols right here would actually be used to represent a transistor-based current source circuit. And since we're not at a level of our circuit analysis where we need to even bother with what the hell transistors are doing or how they work or anything, we're just going to throw a current source in to represent those effects, okay? So this, unlike the voltage sources, is not something that you are actually going to be interacting with on any regular basis until you start doing probably electronics related research or maybe some biomedical research or things like that towards your senior year and or graduate school. We are going to see them very often in our circuit analysis, but that's not something that you are going to physically interact with on any regular basis for the overwhelming majority of you. Okay. All right, so our dependent current sources, we're going to have very similar to what we had with our voltage sources. We're going to have a current controlled current source as well as a voltage controlled current source. And once again, those are just models representing other things, also transistor based actually. So we're going to have the diamond symbol that's telling us that it's a dependent source. There's going to be an arrow indicating the direction of current flow. And I'm going to choose to say that this guy right here is our current controlled current source, or more commonly CCCS. And the magnitude of this current is going to be given by K times IX, where once again we have a scaling factor. For this guy, the scaling factor is in amps per amps or dimensions, right? So it's controlled by a current, so we don't have to multiply it by any units in order to make it output a current. And our controlling variable is the current IX. Lastly, over here on the right, I'm going to have my voltage controlled current source. Once again, it's going to be the exact same symbol. But now I'm going to have my magnitude expressed as lowercase g times some voltage Vx, where this lowercase g has units of amps per volt. Vx is once again my controlling variable. And this is a representation of a voltage controlled current source. Or VCCS. And these guys are my dependent current sources. All right, so before we move on to our next topic, are there any questions regarding current and charge relationships, how we represent currents on our schematic diagrams, or the different types of current sources that we are going to see in this class? Yes, sir. So it's still a voltage source. So the ones that we have in this room are current limited. Actually, one of the most common mistakes that I see are, well, the most common mistake I see is the students forgetting to press the output button so that it doesn't actually generate a voltage, because there's an on button and there's an output button. But then after that, it's students having the current limiting dial turned all the way down that effectively the source can supply no current. So the current that is being supplied by that source is dependent on the load that's connected to it, as well as what that setting on that dial is going to be. So it is not a variable current source. It can just happen to supply different amounts of current depending on what it's connected to. Any other questions? All right, so let's talk about power and energy. So let's start with a mathematical definition for power, okay? So power, P of T. So what did you guys learn about power in your, I don't know, Physics 201 or your high school physics classes or anything like that? What is power? So we're going to get to I times V, absolutely. But what is power generically? It's work done per time, right? So one of the definitions for power, and one that we will wind up using in this class on occasion, is that power is simply the derivative of work or energy with respect to time. Nothing remotely wrong with this relationship. It is 100% true. But we can get a little bit fancy with the math And we can actually split that derivative up. So we could say that dw by dt is the same as dw by dq multiplied by dq by dt, where dw by dq is our voltage as a function of time, and dq by dt is our current as a function of time. So our power will be voltage times current. It's also simply the derivative of energy with respect to time. So our kind of word-based definition here for power is going to be the time rate of change of energy transfer in a circuit element or network. So this is a little bit of circular reasoning here, but I don't really have a better way to do it. Energy, mathematically, is going to be the integral of power. And typically speaking, we are going to wind up integrating over some fixed interval. So I'm going to just say that we're integrating from T1, the time we start worrying about the energy, to T2, the time we're concluding worrying about the energy. And this could further be written as the integral from T1 to T2 of voltage times current with respect to time. And we are going to define energy then as the total amount of power absorbed / supplied, and we'll talk about that in just a moment, over a fixed time interval. Okay. So the in-class assignment problem 2 is all about using these relationships. I'm going to skip that problem because A, I've talked for 75 minutes straight and we still have a mini lab to do. And B, I actually have 2 smaller topics related to power and energy that I want to cover before I let you guys work on the mini lab. Okay. So this first topic is what's called the passive sign convention. And I'm going to sound like a real jackass, like more so than usual here. But I find that this topic is incredibly simple, and I cannot understand for the life of me why you guys make so many damn mistakes on it. I'm going to try to explain it in the easiest way I possibly can. I'm giving you fair warning right now on this second day of class. You are going to see this on damn near every homework assignment and every test throughout this class. So if you do not get it, please, please, please ask questions, or it is going to continuously bite you in the ass for the entire duration of this class. Okay. So, passive sign convention. So I'm going to start with just some generic circuit element here that I'm going to call circuit element A. And I'm going to give it a set of terminals like so. And I'm going to put some ellipses out here. And these ellipses literally just mean that this circuit element A is connected to, it's part of some larger circuit, but we are only interested in what's going on with element A right now. Okay. I'm going to define a voltage drop across element A such that the positive polarity terminal is on top and the negative polarity terminal is on bottom. So this is just my voltage VA. Now I want to be explicitly clear here. I have not said that VA is a positive quantity or it's a negative quantity because I literally do not care. It is just whatever voltage I might happen to measure across this element where I'm assuming the positive polarity to be on top and the negative polarity to be on bottom, okay? Now, I'm going to define the current IA as flowing into the positive polarity term. So my current IA is flowing into the positive polarity terminal, flowing through the element A, and then it is going to flow out of the negative polarity terminal on its path as it goes through this particular circuit element. Are we all catching what I'm throwing there? Okay. So in a configuration like this, where the current is flowing into the positive polarity terminal of a circuit element, the power absorbed is going to be simply the product of VA times IA. The power supplied is going to be negative VA times IA. Let me stop before I go on to the next one. Does that seem difficult? I certainly hope the answer is no, because it's not wildly difficult, right? Anytime we have current flowing into the positive polarity terminal, the product of V and I is giving us absorbed power. And then if we want supplied power, we just need to add a negative sign. Now, let's consider a different scenario. So over here, let's do some circuit element B. This is going to be part of a larger circuit as well. And I'm going to choose to define the voltage across this element B as positive polarity terminal on the bottom. Now I'm going to say that the current IB is flowing into the negative polarity terminal, okay? So we essentially have the opposite case here. So for element A, we had current flowing into the positive polarity terminal, out the negative polarity terminal. Here for element B, we have current flowing into the negative polarity terminal, out the positive polarity terminal. In this particular case, the power supplied by the element is VB times IB, and the power absorbed by the element is negative VB times IB. Okay. So essentially, whenever current is flowing into the negative polarity terminal, supplied power is just the product. And if we want absorbed power, we flip the sign. Okay. So this is the passive sign convention. Okay. Nothing too wildly difficult, I don't think. So what I want us to do now is for us to work in class assignment problem 3. So we are asked specifically to calculate the power absorbed by each element in this particular circuit. So let's start with that 36-volt source on the left, and we're just going to work our way to the right. Okay. So I'm going to put P 36 volts here. Okay. So, $1 million question. What's the voltage drop across the 36-volt source? 36 volts. Great job. What's the current flowing through the 36-volt source? 4 amps. Is that 4 amps of current flowing into the negative polarity terminal or into the positive polarity terminal of that 36-volt source? It's flowing into the negative polarity terminal. So because I'm trying to find absorbed power and my current is flowing into the negative polarity terminal, I need to add a negative sign. So my absorbed power will be negative 36 volts times 4 amps is negative 144 watts. Any questions, comments, or concerns? This literally should be that easy. Yes. So this current IX, it's defined right here, right? So it had to flow out of the positive polarity terminal to be flowing in the direction that's indicated on there. Flowing out of the positive polarity terminal means that it had to flow into the negative polarity terminal first, right? Yep. All right, let's go to element 1. What's the voltage drop across element 1? 12 volts. What's the current flowing through element 1? 4 amps. Is the current flowing into the positive polarity terminal or into the negative polarity terminal? Into the positive polarity terminal. Since I'm calculating absorbed power, I don't need to add a negative sign. So it's just 48 watts. Moving on to element 2. What's the voltage drop across element 2? Yes, ma'am. Sure. So this current IX is flowing out of the positive polarity terminal, right? Which means it had to be flowing into the negative polarity terminal. And because we are calculating absorbed power, if I have current flowing into the negative polarity terminal, I need to use negative V times I. All right, back to element 2. Voltage drop, 24 volts. Current, 2 amps. Is the current flowing into the positive polarity terminal or into the negative polarity terminal? Into the positive, out of the negative? Absolutely right. So we don't need to add a negative sign. Now let's do our current controlled voltage source. So this one is a little bit more tricky just because it's our first time seeing a dependent source in the wild, so to speak. So we are told that the voltage drop across this voltage source is 1 times IX. What are the units on that 1? Go back to your notes from a moment ago if you need to. Volts per amp. So 1 volt per amp times IX. Well, what's IX? 4 amps. So 1 volt per amp times 4 amps is 4 volts. So the voltage source, excuse me, the voltage supplied by that voltage source is just 4 volts, right? So putting it here very explicitly, 1 volt per amp times 4 amps gives us our voltage of 4 volts. What is our current flowing through that voltage source? 2 amps, right? So just for anybody that's not fully seeing it, let me do it in blue here. So we have 2 amps flowing down through element 3. So there has to have been 2 amps up here as well. So that same 2 amps is flowing into the negative polarity terminal of that voltage source and flowing out of the positive polarity terminal. So since the current is flowing into the negative polarity terminal, do I need to add a negative sign to my expression or not? Yes, because I'm calculating absorbed power. So that's going to be -4 volts times 2 amps is -8 watts. And then lastly, I have element 3. So what's the voltage drop across element 3? 28 volts. And then what's the current flowing through element 3? 2 amps. The current is flowing into the positive polarity terminal, out the negative polarity terminal, which means I don't need to add a negative sign. And so I would get 56 watts of absorbed power here. Now, the last topic that I want to talk about, and I'll do this extremely briefly, is just what's called Teligent's theorem. Teligent's theorem simply states that the total sum of the absorbed powers or the total sum of the supplied powers have to equal 0, or another way to put that would be the amount of power absorbed in a circuit or system has to be equal to the amount of power supplied in a circuit or system. That is nothing more than the law of conservation of energy. So if you guys added all of these together, what would you get? You get 0. -144 plus 48 plus 48 minus 8 plus 56 is equal to 0. All of our circuits should always obey Teligent's theorem and by extension, the law of conservation of energy. If they don't, we have made a huge mistake somewhere, okay? So let me just write down Teligent's theorem real quick. Oh, yes. Sure. Well, so it's the coefficient times the current IX. So it told us the voltage there is 1 volt per amp times IX. IX happened to be 4 amps because I told you it was 4 amps. Okay. Yeah. So it's just that coefficient times whatever the controlling variable is, which in this case was 4 amps because it's literally written there in the top left-hand corner of the circuit.
You're always given that they call it 1 is all.
The coefficient. In this case, yeah, it was it would be R because it's a current controlled voltage source. Yeah. So I will try on your exams and stuff like that to give you the units of any of those coefficients just to remind you of things. But there is a reason I went over them on your homeworks from the webworks and all that kind of stuff. It's actually pretty rare for you to be given the units. So there is an expectation that by the time you get around to the test, you will have learned them. Okay, so I'm just going to write down Teligent's theorem here real quick, and then you guys are free to do your mini lab.